So today lecture has to do with the models. So we are still on the theoretical part, let's say, uh, because a model starts from the paper. Okay, I mean, writing down the thoughts, writing down the scope, and then we will see what we need to manage in a model, to manage before create a model. Okay, so the final stage, to be honest, is in a GIS based environment. Okay, because it could be a GIS based environment, it could be um, a programming environment, let's say, like only using a Python in order to solve a model. But before that, we will have to do all the prior preparations properly in order to execute this um, model. Okay, I have two dots here. Okay, weird. Okay, so first of all, what's a model? A model is our need to compute reality. Okay, to make reality more measurable and in order to understand. So whatever is um, I don't know, has a physical meaning or in general meaning in society, it could be modeled. Okay. However, for this, we need to have to let's say to point out its variables. Okay, it depends the aspect of our work, but at the very end, we will have to work with specific variables, parameters, let's say, otherwise. Um, and all of them needs to have a relationship between them. Okay, a direct relationship and indirect relationship. Uh, so here we will have to point out how many of these variables we are going to use and how these variables are going to interact. So the how these variables are going to interact is the rules. Okay, so we will have to build some rules in order for these things to be followed, and by following them or executing them under uh, the GIS, let's say in this kind of situation that we're here and working, it could finally result to a specific um, assumption. And why I say assumptions is because using the models, the final product is a hypothesis, a hypothetical one. Okay, the better the input data, even more less hypothetic the result. Okay, so we will see what we're dealing with. So today we're going to have also some interaction. So don't expect me all the time to talk by myself. It's very weird. So if you have any question in the process, please stop me. You know, put a hand, something that I can see in the screen. And also I will provide you back with some questions for discussion. Okay, so be prepared. Okay, so more or less, there is an abstract, let's say, figure here about the hypothesis on the on the part of the model. And because this PowerPoint is going to be uploaded in the e-class, I have here and there some huge text, let's say, in the PowerPoint for you later to have a check. So these texts are more or less saying the same thing that we're talking here. And it is very important is to understand that our our try to imitate a realistic environment, it cannot be as how to say it now, as much accurate as we understand in the reality. For example, um, a very maybe before saying something on this, um, a question, because I need you to provide me with some knowledge in order to go a little bit further. Does anyone know or can provide me with an idea about the model which you are dealing with these days, or in general you have dealt with? Does anyone have any idea? So we can use it as an example. It could be also a simple model. Okay. No one? You don't have any experience from something that we want to, which has some assumptions and provide some data back. When you want to go out for a field trip, you need to check something first. What's that?
The weather.
The weather. So this is a model, a probabilistic model, which uses some data first, okay, in order to make something realistic, which realistic means the assumption of how it's gonna be the weather. I mean, if it's going to be rainy or windy, the direction of the wind. We will talk later about that. So even this is a model. Okay. So it's an everyday model that we're using. You have already done your own model in the previous semester, as far as I know, which is the digital elevation model, a DM. Okay. This is also another type of model, which is, let's say, more easy to follow and step by step, but still you created a data set, a raster grid file, which has information about elevation in places where you didn't have it, this kind of information in first place. Probably you had some kind of contours, I suppose, some elevation points. Okay, so you had some input data and the model was already fixed and already engineered in the GIS, and you just had to click the buttons. Okay, and to fix the variables. But still, if you try to put things down, you were working under that. Okay, you wanted to make um, a terrain. Okay, a landscape, so something that it is close to reality, and you had to put some variables in there. And you also, not you, in the GIS was already prepared the relationships and the rules. Okay, so a digital elevation model, that's why it's model, okay, and still under this concept. Okay, so be more, let's say, positive. You have already worked with models, more simple models, let's say, but you have this kind of experience. Okay, so now I have two examples to work with. Perfect. Um, Both of them, and I want to keep this uh, word here, is a replica. Okay, and all of these models are a replica of the natural world. So we start dealing with how much close we are to this. Okay, so for that we will have to work later with the accuracy of our data and our hypothesis. So there are several kind of models. Um, we have the deterministic, and the opposite is the stochastic, the static, excuse me, and the dynamic. We have also the empirical models, which sometimes are very useful, and the process-based models, which also is the exact opposite, and the data-driven, with its opposite, the mechanistic. Okay. Okay. Let's say some examples here to understand the differences and what is what. The deterministic models usually are these that have the same input and output. So if we have some data sets that we put in this assumption um, concept, the output will always be the same. Okay. So in this model, there's nothing random, let's say, or probabilistic, let's say. There are specific rules in the deterministic kind of models, and these models can be, how to say it now, re, not placed, replay, re-executed, re-executed by many different users. Okay, so it's very strict, let's say, and always will have the same result. Okay, so given this, does anyone can give me an example on something very strict, very straightforward, and very, you know, very solid? I ask you because I do know that you know it. You have this kind of experience. I know it's Saturday morning is difficult, the hour is difficult after the midweek, but let's let's do our best.
I think the DEM can be a deterministic model.
Perfect, Vasilis. Yes, the DEM, DAM, DTM, DSM, the surface models. All these kind of models are deterministic models. Okay, the hydrological flow direction, which we can create it from a DEM, the hillside. I think you have done this kind of exercise, huh? You created rasters files from raster grids, right? He'll say the aspect in the GIS of a slope.
Yes, we did that.
Perfect. Um, the slope itself, I mean, it's also a deterministic model. Okay. So strict input, strict output. Let's keep that simple in our mind. The opposite is the stochastic model. Here we have models where they are working with data. Um, each time they're running, let's say, algorithms where are a little bit on the verge of the probabilistic and the randomness, let's say. The output in these cases is always different, even if you provide the same input. Um, Usually, these models are working with distributions, let's say, the results here and there, and they are working with how the data are distributed somewhere. Okay, and I'm just trying to be a little bit vague in order to cover whatever can fit in here. Okay, and here we're from because we are talking about randomness, we have also the uncertainty, the modeling uncertainty. Okay, so mm, probably you have heard about the Kriging methodology. If not, we will do it here. As a three parameter variable methodology, um, which Kriging is a statistical analysis of our data, and because of this statistical analysis in the space is providing, let's say, results uh, because of this, let's say, a relationship only on mathematics and only on assumptions that if in this place I have enough data, then the result could be like that. But this always can change, okay, in every kind of running this kind of models. Thus, Kriging is a methodology where you can create raster grid data sets from other vector data sets where mm, you have enough data. Um, the more data you have, the better the result and less uncertainty in this kind of model. Uh, Another kind of uh, example for these models is the probabilistic hazard models. All these models, the probabilistic ones, they are working with if this variable change with this specific way, then the result will be like that. Okay, so this kind of probabilistic hazard models, they are containing a lot of variables that are, I mean, that's why they are variables, that change in the time. Okay, so still here we have another kind of uncertainty. And another example of this kind of stochastic models is the Monte Carlo simulation. That's, let's say, the title of that. So for this, I would prefer you to do a research about what's the Monte Carlo. Let's Monte Carlo. I mean, um, because I think it's a little bit difficult to explain verbally. And it's better to do it by research. So write down to search about the Monte Carlo simulations.
Can you say the
Uh,
name again?
Monte Carlo.
Monte Carlo.
Monte Carlo. Monte Carlo, like the song. And the town. Monte Carlo simulations as stochastic models. Let's say it's a small homework. Okay. Well, you will have enough things to read after that. Sorry for this. Uh, so, to conclude on this, okay, we have deterministic as certainty, and stochastic as uncertainty aware. Okay, we keep these as bullets. Well, stochastic is also a Greek word, to be honest. So somehow we do understand this. But yeah, so any questions on this? I'm just, you know, trying to go through all of these, and at the end, at the second half of our today lecture, we're going to work with a specific um, model. We will see later what kind of model is this. So, I don't see any some hands, no? To be honest, you are eight, and I see only three people. Sometimes it's good to see all of you. I mean, your faces. Just mentioning. Okay. We have also the static and dynamic. So static are models that are referring to a moment uh, and they don't change through time. Okay. So we don't have any time evolution. It's like photographing a specific condition. Okay. Um, I think that you have seen these kind of models also, or you may have heard about them. Static models, not changing time. Any proposal? After, okay, we have a natural phenomenon. After this natural phenomena, we have a change, let's say, on the Earth's surface. Okay, and we have to model, maybe to map, let's say, the problems
Earthquakes.
Earthquakes. The earthquakes can also be a static. Not all, well, the earthquakes can be both. I mean, they can be deterministic, they can be stochastic, and also they can be static. But have a better example. In an area that we expect to get flooded, for example, the variables are very specific. I mean, they're geomorphological, so, they're um, social. There we have the land cover. Okay, so in this kind of analysis, which is a flood risk, so in general, risk analysis can be a static analysis. Why? Because this can be changed in time. So you will have to freeze, let's say, the time in order to have the specific variables on this specific time, okay, in order to do this analysis. For example, you have a different flood risk analysis in an area which has a forest, okay. For those who are a little bit aware of these events, we had some fires on the northern part of Evia Island, which the whole northern part was burned in 220. Okay, so before the fires, the flood risk assessment or analysis or the model, you can call it whatever you want, it was different like after the fire. Okay, so we had there a change in the variable and change in through time. So that's why we have to froze the time, check the variable, and work on these variables for that specific time. This is very important because when you do this kind of models and this kind of analysis, you will have to be very specific on which data you work on and when, specifically when.
Can I
Okay?
add something?
Yes.
It's also the same with fire risk analysis. Because the variable is not static. The variable, a variable for fire may be, for example, the wind, which is not static.
It's not, no. It's not the same. It's not static because the fires has to be done, let's say, on they need the material, okay? They need the material, and also they need different conditions in order to occur or not, let's say. So this could be, let's say, a little bit more on the dynamic part, where I would like to go later. And also on you can run also stochastic models also for this. If that, then what? Okay. It depends what kind of you can run different models for the same thing. I mean, but you will have different results. Okay. It depends what you want to work on. Okay, or how. Another example for this static generalized is any kind of suitability map. Suitability to build a building in that place. Okay, so all these kind of variables are stopped in time. That's why it's static. Okay, everything is stopped in time, and you're taking into account these variables. For example, if you want to make again, I forgot this word. Uh,
To
okay.
replicate.
Huh?
To replicate, you mean?
No, no,
To
no.
do it
It's very
again and
specific.
again.
Where we put our garbages for proper treatment, landfill for landfills. Okay, for environmental landfills, let's say, there's very specific, there are many specific rules that you have to point where to build this, to make a suitability map in order to build this kind of building. I mean, it's a whole thing. So these rules are very static, they're taking account specific variables under specific conditions. So you will have to take in account this. For example, a variable that changes through time is the land uses and the land cover. Okay, so you have whatever has land uses and land cover, you have to take in account that specific moment, this specific data set. Okay, I hope this is a little bit understood. I mean, for example, we are living in a town which is uh, built up very fast. Okay, so the land cover changes through time. Okay, the borders of the town change. So we will have to do this kind of suitability map for whatever, for a hospital. For example, on that specific moment, if we do it 5 years later, maybe or probably, we will have to take in account new data sets. Okay. So on the other hand, we have the dynamic models. So this kind of models take in account time. Okay. And they are working with um, this time passing evolution or some simulation processes. Okay, whatever is working with simulation. So before I said that we need to be static in order to do the suitability analysis, a suitability map. Okay, but if we want to work not with something specific, but to see the changes through time, so the urban growth, for example, then we are working with something dynamic. Okay, so same data sets, let's say, but different managing. Mm, okay, previous we said about the flood risk. The flood risk is, let's say, the flood risk for this area on 2023 is that. And you get a map where you have some values of risk. Okay, and we will see later on about this kind of values in this kind of models. But if you want to talk about the flood propagation, okay, or something that which propagation is something that changes through time, then you're going to the dynamic model. So in this kind of case, let's say is like having many static models all together. Okay. I'm trying to think a little bit more of examples. Or okay, no, I won't flood you with more data. Just keep in mind that static and dynamic, the static is answering in the question, what is, okay, what is the result because of these variables. And then dynamic answers to the question, how it evolves. Okay, so if you want to answer these questions, you have to check your specific model that you want to build or work on. Okay.
So the weather is a dynamic model.
Yeah.
Okay.
It's a dynamic, it's a stochastic first because it works on statistics because of the samples, let's say samples, the data sets that you have from the past for this specific, let's say, area. Let's point out Athens. Okay. For Athens, you have many data sets in the past. They are analyzed under algorithms about the time and condition. Okay, the space is I mean specific Athens. Okay, so time and condition. So in the case of stochastic, you get as a result the condition, the weather. Okay, but in the dynamic, you also work with the condition and time together. That time period, you will have this condition. If you change the time, you will have a different condition. But the condition is a result of the stochastic. So that's why we say that the weather models are sophisticated and complex. That okay? So they're working on two, let's say, kind of modeling procedures. But nowadays they are very advanced. I mean, you have seen it. In the past, we were like, okay, what the model says, this result. It's going to rain. Okay, it won't. So we were like that. So they had a very, let's go back to this, a very high, um, not error, uncertainty. Okay, uncertainty. That's a word. But now the uncertainty is less. And as the technology, mathematics, algorithms, AI now are advancing, this uncertainty is become less and less and less. Okay. And also we have even more samples data. I mean, the weather data as time passes. Okay, because it's dynamic. So all these are working in favor to us. Other question? Very good on time. So let's go to the empirical. Empirical models, you may have heard about that, are based on observations and data. So in here we have high influence of the researcher, the the person who is providing the data. So it's not only mathematics and algorithms and something like that, but we are getting a lot of human, let's say, based quality assessment and etc. So we have some statistical relationships here in this kind of models. They are not, it's not obliged to have a physical understanding, let's say. So it could be some generalized. And in this kind of models, we can say is the machine learning kind of models, the analytical hierarchy process, which is the one, I said it, we are going to see later on. Okay, so the machine learning, you have the statistical relationships of the data, but someone is providing the data, okay, or the path to the model to how to learn or what to learn, okay. So here we have the human-based influence. Also, the analytical hierarchy process, which is a very good example to work on. We will see later how it goes. So we have a relationship, mathematical one, but someone is providing the data. And this data, this someone is us, probably. Or will be. So the opposite is the process-based models. Okay, so here we will have, we don't do assumptions, we don't select, let's say, the relationships. Okay, but here we have natural laws in this case. So their characteristics are more physical driven, let's say, okay, and the relationships are causal. So in this kind of models, we can put, let's say, mm, all the natural conditions models. So hydrological models, okay? Very simple. We have a river, we have rainfall, we have this kind of soil, let's say, the groundwater depth is this, specific numbers, okay? So all of that, all of these parameters are physical parameters, okay? They're standard parameters. So the model will provide you a physical and standard result. So sometimes we can say that the process-based models are very connected to the deterministic models, okay? Some of the deterministic kind of models are connected to the process-based models. Another example of process-based is the erosion, for example. Coastal erosion, soil erosion, runoff erosion, of rock weathering, all of these kind of models, okay? Because the conditions are based on natural laws. An example, the coastal erosion. You have the waves, natural, okay? You have the currents. You have the sea level change, okay? The sea level rise, okay? This is still natural. You have the type of the sediment, okay, for the beach, okay? All of these are natural parameters. They have specific um, numerical, let's say, um, parameters for each parameter. Okay, um, what else? The groundwater flow. Okay, another example. It needs the slope as a variable. It needs also the type of soil, the type of rock. Another thing. Okay, if you want to drill and make some wells. Okay, so even this is a process-based model which is under natural laws. Okay. I will say it again, I will repeat it, that it doesn't mean an example that we're using on a specific kind of models, that it does not fit also to other kind of models. Okay, they fit, but the result will be different. I can do erosion model, let's say an example, but if I put the kind of time change, I can make it from process based to a dynamic. And if I make also some assumptions of changes in other kind of conditions, except the natural laws, then from process-based that I went to dynamic, I can also combine with stochastic. Okay, and if all of these I can provide it to a machine learning system, then the final model could be empirical. So as you see, you build a process, okay, until you reach to a final result. So it depends on what kind of model you work on the specific stage and how. Okay, and everything can be, to be honest, can be combined at the end, but it will be huge. So, um, some bullets to also make the changes between empirical and process-based. So in the empirical, we have, let's say, assumptions that fits the data. So we do know the data and we make fit them in this kind of model. But the process-based models are, let's say, explaining the system. Okay, so the natural system. They are explaining processes. They are explaining conditions. Okay, at the end. Oh, not yet. So, question on this? I hope the examples that I find to be helpful. Okay. Data driven. Sometimes these kind of models are a little bit confused with the previous one. So this model is, let's say, produced from the previous analysis, okay, from the empirical one. Uh, let's say is the result of a machine learning, okay, analysis model. Is a model where in which we can find patterns between variables. Okay, uh, so here we have something more sophisticated. Maybe you have heard the term neural networks. So this kind of um, algorithms, final algorithms, are working on this kind of models. And what I don't want to go deep on that. First, because my own knowledge are not very deep on this, and this is could be a whole um, kind of course in a master program. So just keep in mind that this is, let's say, a final stage of analysis which is produced from other models. It cannot be done by itself. Okay. If you want to do a homework also on that, and I would suggest to do it because it's good to understand which kind of tools we have on our hands. Okay, because after that you can do your own research and you will have to understand what kind of models you are going to work on. So neural networks are working on this kind of data-driven are not data-driven models. On the other hand, we have the mechanistic kind of models, which is based on known mechanisms. So let's say on equations, simple equations, or explicit equations. So in this kind of case, it's very easy for someone to read, to understand this kind of model. Um, like the hydraulic models, okay, which can be also a little bit correlated also with the process-based, let's say, okay. But still here, we can say that we put a little bit more engineering laws. So in the hydraulic models, you have specific equations giving how the water will flow in the soil. Okay, so you give these kind of equations in your model. Also, any kind of stability models. Okay, rock stability, earth soil stability, the house stability models, building stability models, construction stability. All these kind of stability models are under the mechanistic kind of models, okay? Because there are equations in all these kind of situations, and these equations should be considered in your model, okay?
Can I ask something?
Questions?
The mechanistic model, isn't it very similar to the deterministic?
Not to be exactly, it's more close to the process-based, because some processes, and I will tell you why, some processes may have also equations. Okay, they're very, very, very specific. So this process-based can be very correlated to the mechanistic kind of models. The deterministic kind of model, let's say there is a part of speculation. Okay, a small, but there's still some kind of speculation. So it does not run on specific equations, but on some kind of deterministic. I say the same word. How to say? No, speculations. This is the word, speculations. Yeah. The mechanistic won't give you something hypothetical. It will
So in the deterministic model, we make some speculations that we assume that they are correct.
exactly. Like, have it in mind the DM, okay, which is a very simple example. The DM. You know that the contour here is the 100. You know that here you have the sea level. And this model, because it understands the whole relationship between the data, it provides you even more data. It creates even more data between those two contours, for example. Okay, it assumes that between them you have values from higher than 0, less than 100. Okay, but the mechanistic won't do that. The mechanistic will say, here you have 50. Okay? Very specific. It's very specific, this kind of models. Because I ran this kind of equation, which is the one that we provided in this model.
So in the deterministic, as we make we said we make assumptions. We have to be very sure that the probability of this assumption is correct in order the model to be correct.
Well, usually the deterministic model are very specific models. Okay, they are run specific algorithms. Their main characteristic that you need to keep in mind is that you provide a specific input, okay, a data input, and they always will do the same assumption, and you will get the same output.
Oh, okay. Okay.
Still have some assumptions, but the output will be the same. Rather than the stochastic, which will all the time these kind of models are, let's say, depending their execution will provide you a slightly different, or I don't know, maybe you can get also high differences on the result. Okay.
Yes.
That's why I mentioned that the process-based models can sometimes be like mechanistic. So for some, okay, I gave an example of the coastal erosion, okay, about the process-based, and this was without giving any equation. But there, in the past, was a methodology um, which was called come on, I forgot the name. CVI, Coastal Vulnerability Index, okay, which the Coastal Vulnerability Index was a very specific equation. 6 parameters, okay, whatever kind of variables, no, excuse me, not whatever, specific variables under root something. Well, it was an equation. You executed this equation, and then you were getting the result of the values. So this was a process-based, let's say, model, but under mechanistic specific uh, methodology. This, let's say, made it a little bit less accurate because each variable, which was a process variable, um, maybe, excuse me, the one who made the CVI, this kind of index, had to make a big assumption, okay, that all these variables always will work with a specific equation. So this, let's say, made this model very vague, okay, and less accurate. Nowadays, we are dealing with a different kind of modeling for runoff erosion in order to get out from this kind of non-accurate loop. Sometimes you need to do it if you want not high resolution results. Okay, so we are not negative to or opposite to models that they are not very accurate. Okay, it depends what you want when you want. Okay, this slide took enough time. So I have a couple of slides here for reading later, not now. But here we are talking and dealing with the modeling and the planning of the of how to create this model. Okay. First, as I mentioned, that we need to put all the variables with a specific relationships on the paper, and then conclude on what we are going to use, how we are going to use, and where in the model. Okay, so I go further from that. Also, this is the same thing. And we go to the workflow. All good and nice. I mean, with the models and all of these things that we talked. But when you are building a model from the scratch, let's say, you will have to think about it. Okay. And first of all, you have to find a problem, to define the problem. What is the thing that I need to solve or to answer? Okay. So that's why previous with the kind of models you in some of these models you heard me putting some questions. When this change, for example, what was that change? Okay, so depending the kind of questions that you want to answer, you will have to do this, let's say, definition in the first stage. I want to see how much is the erosion. How much is the erosion? But in the erosion, for example, I can say how the erosion changes. Okay, this changes the models. Okay, so we will have to be very specific on that. For sure, after having this, we can proceed with the model, let's say, acquisition. Okay, or the models. Maybe you will have to use a deterministic model, and this will provide data for a data-driven model, a neural network. Okay, and these results have to be analyzed by us. I mean, the GIS experts or the scientist, the engineer, whatever. Then we're going to the hard part. All this were easy. The hard part is the data acquisition. And as we have already discussed, some datasets will need, could be open. Some other datasets needs to be provided by other parties, or other datasets can be acquired by us. Okay. This might affect the accuracy of the model. Different datasets from different sources may have different accuracy. For example, we want to make an acceptability map about a hotel. Okay. So we need data from the geological survey of the area, okay, which these data are not very accurate. I mean, it's data sets with 1 to 50,000, for example. But we need also some topographic data, which an engineer will go there and get a GNSS RTK and will get all the topographic altitudes, measurements with the laser scanner, I mean, all of these things. And these data sets have high accuracy. So we are dealing with two different data sets, okay, in the model, and some of them, depending which is the most important, may affect the final result, okay. However, data acquisition is something very tricky and is considered very crucial about the later on evolution of our work, let's say. Okay. Model implementation. So here we will have to run the model that we selected. Okay. We put the data here in the process that we have finalized, and we proceed. But the result is not finalized. Maybe we will have to run some trial and errors in order to see if the model run with the optimal, let's say, way. So we will have to validate the result. If we have some not accurate results, we will have to run again, to go again back to the fourth part. So here, this process is a back and forth all the time. 456, back 456, back 456, until the validation is, let's say, more I cannot find the word, to be honest. Suitable for our results, and then we can run the whole model again with a specific scenario and see how it will go. Okay. A tip on the models is that if we are running our own model that is not tried again in the past, it's better to do it with simple data sets and see how it goes. So this procedure, the implementation, calibration, validation, can be faster. Okay. So once this is assured, then we can run with the proper data sets, let's say, as a scenario simulation. Okay. Questions on this? Okay, very good. So it depends what we want to do. Okay, so we have models about society, social models. We have models on physical parts, so we consider them as geographical, geological, hazard, models for policy making. We have also finance. Don't forget about the finance, logistic models. So depending the situation, we have different kind of models. Okay, that can get uh, under the umbrella of a model. So uncertainty, in case that we do have this kind, we have the data uncertainty. If the data sets are not, let's say, accurate. Okay, it depends also the scale of creation. We have the structure, the specific structure of the model. It had some, we talked about it before while going through all these kind of models, but every each of these models, they have their, let's say, luck point, let's say, which rises some kind of uncertainty. The parameters that we're going to use, all the time we don't use the same parameters, okay, except it is mechanistic, so it's very specific. So one parameter can be very accurate. For example, the altitude, okay, it's very accurate. I mean, it's something very specific, the altitude. But there are other parameters that varies, like the temperature, okay. Yeah. Okay. The other two, as let's say, they're provided from the first three. Okay. The error propagations, as I think you understand that if you have some uncertainty in the first place and then you create data sets that are weak, let's say, you let's say create data sets with some errors, and this error, if it goes further, okay, with another process, it becomes even bigger. Okay, so if you have problem in the first case, which let's say we can count it as, we can, if we can put a value, let's say we can say that is 1, then on the process the 1 can become 5. Okay, so that's why we have the error propagation in the models. And sometimes you need to use also confidence map, which means where you have high confidence of your data sets and the results, and where you have less confidence. So in this kind of in this kind of models, you need to be very specific about the confidence in general. Okay. Otherwise, for example, if you are going uh, to publish a paper, it won't be uh, how to say, properly, maybe not properly. It won't be accepted, to be honest, in case you don't have some kind of confidence analysis on your datasets. Okay, so sometimes you need to put also your statistical uncertainties in this case, if there is any. It depends the kind of model. Okay. We're on this part. Yep. Okay, so it's a time for break because after that we have to brainstorm. Storm, really. Okay, so 1/4 of break, huh? Yeah.
Okay.
Okay.
So we're going back at 11:35. Okay.
Yes.
Okay.
See you in a while. Okay, good. So we go to this example. This model is one of the oldest, I can say, models. Okay. Is called analytic hierarchy process. And as a model, it is, let's say, considered, where's the models to see, as an empirical one. Okay. And you will understand why we call it empirical one. So it's one of the most, let's say, widespread and wide used models, as it is based on a decision-making tool. Okay, so whatever it can gain a qualitative and quantitative value, it can be processed under AHP. But the one who is going to use the AHP should be also the data analyst, not just someone who is going to execute it. Okay. So okay. Before going to that, I must say that another thing is a multi-criteria decision model. Okay. So you provide, in order to work well, you need to provide different criteria in this model. It is also working as a pairwise comparison. between the criterias. It produces some weights on these criterias, and then it analyzes the final result. The analysis of the result is being through the, I don't know if you remember from the school, if you have done it since then, the eigenvalues, the eigenvectors, eigenvalues, eigen, I don't know if I still pronounce it very well, but the eigen mathematics. Okay, it's algebra. So if you do a homework on that, it will be even better for you to understand how this model is working. Okay, and we will see some already prepared mathematics solved from me in order to work on this. So we have this eigenvalue pairwise comparison. So as a final result, we get some calibrated values. These calibration values are, as I mentioned, based on the quantity of your data, but also on the quality of your data. We will see. It is already prepared, let's say, from the scientist who built this model. The scale of this model values goes from 1 to 9, and this scale, it, as I mentioned, is a pairwise comparison, so you will have to compare each variable or criteria, whatever, between them. So if the value is the quality is equal, then you will have to put the one as a value. Okay, so if one criteria is more important than the other one, so it gets the highest value of 9. If it's something in between, we will see later on a specific table. So this is the spectrum of the comparison, and this comparison is analyzed under the eigenvalues approach for the final result. So there is an assumption of each criteria independent. We, as I mentioned, get insensitive to the weights and sensitivity to the weights that we provided. It depends also the subject that you analyze, so it's not something that is fixed in any kind of case, and also is very sensitive on the scale. Okay, so the bigger scale, the larger scale, the less, let's say, accuracy on these results, and you can understand how it goes. So here we still have a similar methodology in order to build and solve this kind of model. First, we have to state the problem. Which is the problem? Excuse me. One thing that I forgot to say that is analytical hierarchy process is a very optimal, let's say, optimum methodology to work with hazard mapping. Okay. If you work with hazards, whatever kind of this hazard, AHP is one of the models that you can use on that. However, I have read also another, let's say, study that they used it in order to have a decision about which school is better for a household for their children, let's say. So it depends how you use it. Also, you will have to do some homework on that. I will give you instructions later on an email about what to read. I have also collected some bibliography in the documents that you should go there and have some homework on this. But I will give you also instructions how to search about the AHP and this kind of broad models. Okay, so first we will have, secondly, the first we talked about it. Secondly, we will have to visualize a little bit the upcoming result. You cannot proceed with a model if you go executing it blindly. Okay, you expect something just in order to have, you know, a target, only to this. But you can foresee, let's say, a little bit the outcome. So having this in mind, you can validate later on your data and your analysis, because you will have to correct your methodology in the process. So we identify the criteria that we're going to work with, okay? And if we cannot do it, maybe we can ask about an expert on this specific subject. I don't know which this is. I'm saying just broadly. Is to see the influence between the behavior of each criteria. For example, a geologist can provide um, the influence about a rock type, okay? But if you are running a socio-economic AHP model, then you need someone expertise on finance, on managing, I don't know. You understand what I mean? So it depends who is the analyst. So here we need the influence categorization. And depending on the final result, we will have to build our model here, having in mind this specific goal. So to have this specific criteria, and also how these criteria are interacting between them. Sometimes the same criteria having different goal may interact with different way. Okay, so we have to be very precise about what we are going to do this model. So okay, I will leave you these. Okay, the 5 is talking about the a constitute in the equation that we are going to use later, where this is affecting the accuracy of the final result. The more criteria you have, the less accuracy you have in this case. So it's a little bit fuzzy sometimes. But with AHP, if you have, for example, 7 criteria, excuse me, try to solve this with 7 instead of 8 or 5. So the less comparisons you have to do, because this will give you a number, the less comparisons you have to do, the higher the accuracy. Okay. But if you have only, for example, a bivariate comparison, only 2 aspects, this is not the optimum for a model to be called a model. So somewhere between is the truth, let's say, on how many variables you may use in this model. Okay, but you will see later how it works. After having that, then we perform the maximum eigenvalues algebra in order to first on that and then on normalized values in order to get the proper criteria weighting. And then we will have to validate if our comparison was correct. This is done using specific eigenvalue equations for this satisfactory decision about our criterion. If this number is not appropriate, then we will have to go back, rearrange probably the dataset interaction and the values, and then go again with our calculations. I will show you. So the one who made all this, let's say, interesting model is Saty et al. On 1980. To be honest, I have read another paper of him at 1977. So the idea started since 77, and on 80 he finalized this idea about this developing of the hierarchy breaking assumption process, and also validating under algebra. And also how to put weights, proper weights on different attributes. So here we see how to numerically judge the maybe to numerically have the comparison between 2 variables, 2 criteria. Okay, so if it's big enough. So if 2 criteria have equal importance, it gets the value 1. Okay, if the first criteria to the second, and this is important, how you read this comparison. So the first criteria to the second criteria is a little bit moderately more important, then gets the value 3. And you see how it goes. If you are not sure and you are somewhere in between these characterizations, then you can put the numbers 2, 4, 6, and 8. Okay.
May I ask something?
So it's a rational way of thinking, let's say.
Can I ask something?
Of course.
I didn't understand if do we give these values 1, 3, 5, 7 up to 9, or the model gives these numbers, this
This
way?
is the part where human intervenes in this model. We put it, we or the analyst, it depends, you know, it depends the case.
So what did Eigen do actually? I don't
It's
understand.
later. It is later on. First, you have to put the criteria, let's say, connection, and then the eigenvalues are starting putting the weights. Okay, after you put this number are not the weights. This is the pairwise comparison.
Okay.
Later on, we built a table with the criteria on with these comparisons, and after this table, we have the eigenvalues start working on in order to
And
get
how do we give these values from bibliography? I mean,
big bibliography, our knowledge, and that's why we say here that um, this kind of model is on the part. I forgot again the word. That's why I will put this. It's an empirical on
okay.
this part because you have human intervention, you have the human knowledge which has to put this kind of definitions between the comparisons of two variables. So if you are not well, how to say,
Expert on some on this.
yes, let's say if you're not expert on a specific subject, then you may not have good accuracy. But the good thing is that in this kind of model, at the end, you have a validation process. So if your assumptions are wrong, the validation will show it to you because of the Indian vector, and then you will have to come back to this table and rearrange your definitions.
Okay. Okay.
It is fun, but it's not very easy to correct it, to be honest.
Okay.
Not like correcting one number, it will affect the final result because of the table version um, data consistency. I, I will show you later. I'm just, going a little bit theoretically and we will see practically. Okay.
Okay.
And you see, still we're talking about the paper. I mean, desk work. We haven't used them in the GIS. Ah, excuse me. I had it also here in this final bullet. So at the end, we do a consistency check about our assumptions. Okay, so that's a good thing. Okay, here I have an example from the SATIs. That's why you see also this kind of fonts from the SATI paper about how he managed information and the whole numerical um, matching. Okay, so the first question was about to choose the best college. Okay, so which are the criteria to choose the best college? Okay, is the location not far, not so much, the ambience of the college, the reputation of the college. Okay, this was in USA, so reputation sometimes is very important, and the academics who are in the college. Okay, so what are the selections that we have in our position? Is the Swarthmore, the Nosworth, whatever, five different colleges. Okay, so criteria, colleges, and the question. And here we have the table. So we put on the vertical and the horizontal and the vertical, we put the same criteria, and then we see the interaction between them. The first criteria which we compare is the vertical one to the horizontal one. This is how we ask the question. So the location, how much important is on the location? It's the same thing, so it's equal, so it gets the number 1. The ambience, how much important is to the location? For the user was 7, a lot more important the ambience to the location. It worth, let's say, driving to go there. Okay. The reputation of the college, how much important was to the location? 5. And the same goes also for the academics. So here we answered, we did a pairwise, 4 pairwise comparisons between all the criteria to the location. And we do the same thing for the ambience, the same thing for the reputation, and the same thing for the academics. Okay.
Can we give the same value to to two different pairwise
Yes, of course. It doesn't. You're not obliged to use one number different and then change. You know, you don't. You can. Everything can be equal. For example, it could be. I have never seen that, to be honest, because there is no point to use eigenvector if everything is equal. You are doing an equation, but let's say.
Okay.
At what point it's easier, because if you correlate the same thing, it gets the number 1. Okay, abins to abins 1, reputation to reputation 1. So if you do once all, do I have a pen here? Give me a moment. I think this is better. Okay. Come on. Okay. If you do the comparison once, oh, perfect. The rest is just the opposite. Okay, so for example, you have here the ambience, which is to the location 7. So the location to the ambience, it cannot have a different number, but just the opposite. So it's 1 to 7th. Okay. The same goes also for the reputation. Reputation to location is 5. Location to the reputation is 1 divided to 5. Okay. Do we get this? So once you do, let's say, a full scale comparison, the others are just the opposite. Okay. So below, I have to somehow do. Okay. So below we have also the comparison between the different locations. Okay, between them. So the Swarth, Northwold, and etc. So all of these are getting other values. The CR is the consistency ratio, which is also calculated by the eigenvector. And after that, you have the calculation of the weight, WT. I will show you later also the mathematics. Okay, so as we understand, the AHP has some advantages, okay, and disadvantages. First is very flexible. You can put whatever your hypothesis is, just having some logic, okay, in that. Um, Also, you can integrate it different methodologies like programming or like fuzzy logic if you want to make some more complicated pairwise comparisons or many comparisons on the same time. So you can, let's say, broaden it a little bit and make it more mechanistic. Okay, this is the first that I mentioned. And the other thing that has is that enables the researchers to arrange different alternatives so you can change it as you want. Okay, the variables. If it doesn't work with the way you imagine, then you can change their interaction. Okay, and you can see live, let's say, how this affect your model. So this is a very good thing. It's a very strong, let's say, card that you can play with this kind of methodology. So later you can take some decisions about which, um, let's say, pair of comparison you can proceed with. But of course, there's also some limitations. So you cannot deal independently with each criteria. For example, if you think later on that some of your comparisons weren't correct between two criteria, and you may go change their correlate the number. This may affect the whole structure and won't provide you the consistency result that you wanted. So you will have to undo and do it from the very beginning. Okay. And also you have a very limited number of alternatives to do on the same time. You cannot deal with different things because the question is only one, let's say, at the very beginning. So you will have to work with this and to solve the model. Our example that we are going to work today in order to understand how this works, okay, we have time, is the flood hazard. Okay. For this flood hazard, though, we will work with environmental parameters. Uh, excuse me, this is not what we will do today, full. It's a part that we're going to do today, but the rest is going to be done by you as an exercise for the next time. Because we have first the environmental parameters, okay, which is, let's say, a table, a specific table of comparing these variables. So we have the rainfall, we have as a variable the river density, how many rivers we have in an area, okay. We have the slope, we have the elevation, we have the land use, land cover, because it's something that affects the flood. If you have artificial surfaces like the town, you have higher risk of flood, okay, rather than a bare soil area. And of course, the soil permeability, the type of soil which can absorb or not enough water. If absorbs enough water, then you don't have the flood, which is on the surface. Okay, just simple understanding on the process based. But also we have another variable, which is the social parameter. So it depends the total population. If you have few people, the hazard is less. If you have many people, the hazard is higher. The population density, where are these people located, concentrated? The distance of the infrastructure. This is also another thing that affects the hazard. Of course, the land use and land cover, but on the social point of view, the distance to road, okay, which roads are essential because they are leading to safety areas, okay, and of course there is distance from river banks, okay. So this is from the social parameter. So we have two different parameters, and later on we will join all these parameters in order to make the final decision about our model. Okay, we talk about that. So, any question so far? Okay. I stop the share here.
Can I ask something?
Of course, while I'm dealing with the PowerPoint.
The
Yes.
total number of variables are more, I think like 10.
Mm-hmm.
Aren't they too many for this model? You said
Yes.
that it's about the optimum. It's like optimal. It's about like 5, 6. I don't know, something like that. I understood.
By my knowledge and experience, I think is around 5.
Okay.
5 to 6 are enough, let's say the golden ratio, from the perspective of the accuracy, from the perspective of your effort, because you can imagine
Mhm.
if you have many, you have more multiplications, let's say, like if you have 6 to 6, you have to do 36 different comparisons. Okay, not exactly, it is around 20. I mean, the other one is just the opposite of the first that you did. But still, the more assumptions you do, the higher probability you have to not have a proper accuracy in your model.
So why do we
So,
use this model?
huh?
Why do we use this model, not another one?
Because it's very easy to work with, it's very easy to explain um, how you put the weights, because it has also some mathematics. It also gives you a feedback, and we will see it, about if your rational thinking was correct. So other models you can just run. For example, computing models may run for forever, and you wait for 2 days until you get nothing. And then you have to remodel these models. Here, we haven't used any technology yet. We are working, and you will see just an Excel table in order to have things here and there, already prepare the equations and work on this. Just, just a puzzling, let's say. Okay.
Okay.
So I suppose a 5 to 6 um, variables are enough, are good for the accuracy and also to, for example, for someone who is not, maybe no, it depends what you want to do with this model. If you want to use it and provide the results just for a report, whatever is good. If you want to use this model to produce a paper for a spatial analysis and give it to a very good publish it in a very good journal, here they are not very satisfied with small models. They want a satisfactory, let's say, amount of variables. Otherwise, they say it's too simplistic. Okay, so you will have to judge what you want to do with your model, or to use first an AHP to get some weights, to get some understanding, and then provide the result to a more sophisticated mechanical model, for example. It depends. Yeah. So now we're going back to Excel. Mm, uh, screen. Do you see my screen, and how big do you see my letters? This is the crucial question. Is it readable?
Ah,
For me,
so
no.
neither for me.
Okay, so give me a moment. I will have to change screens. I will put that here. Here. So now it's better? Hmm?
No,
No.
no.
These are okay.
For me, yes.
Okay, so here the problem is just the zoom because this is a little bit big. I put it here just like in order to read. So what we want to do, excuse me, because now it's on my second screen, I have to look there, okay? So excuse my angle of my head. So first of all, we have to put in levels our questions and our analysis, okay, and variables. The first, the first level is what we want to do. We want to do a flood vulnerability assessment, okay, an analysis, a spatial analysis on flood. Okay. So for this, we need two other factors. We need the physical factor, so the perspective from the part of the land, okay, and also the socioeconomic factors, those who affect the people, okay. So two different. So this is the level two. And for each of them, we need to identify the criteria. Some of them may have the same criteria, but different read, let's say. Okay, so on level three, we have, in this case, the elevation, okay, as a physical variable. We have the land use land cover, look, the hydrolithology vulnerability. This is something that someone has to provide it, to us, or we can do some openly assumptions. So this variable is, now we have also the AI. AI may also help in this kind of information. Don't forget that. I forget that. So we will have a soil or a rock. So the condition of the soil and the rock will change its hydrological idiotities, abilities. Okay, so this has a numerical, let's say, aspect. So we have to understand here one kind of geology or one kind of soil we have in order to validate how much water is going to infiltrate or not on this on the specific areas. Okay, so now that we have also the AI, this is something that may help you in case of you find, for example, different kind of rocks like limestones in your area, and you have also conglomerates, for example. Okay, both of them have total different hydrological abilities. So the AI, suppose it can validate this and provide you which has more or less of this ability. Okay, the slope, we do understand high slope, high velocities of the water. Okay, lower the slope, low velocities of the water. Okay, uh, here is distance from rivers. I remember. The dr is the distance from rivers. Here is the drainage density. Okay, so how many rivers you have in a specific space, and also of course the rainfall. Okay, the one who is producing the flood. And for the socioeconomic, here we have the distance to roads, the house density because this is another information that you may have provided from some authorities. If you don't find this, you can put people density. This is also that's something that works. Okay. Um, okay. For this socioeconomic factor, we selected also the distance from archaeological sites, which is also something that is important that we don't want to be destroyed for a profound flood. Okay, and of course, again, the land use, land cover in this case. So, two different factors. We work with these factors separately. Okay, all good on this? Okay, so now, Sati, let's say, said that if you want to validate your results, okay, you will have to know that it depends of your number of factors that you are working on. So n is the number of factors that you are working, okay, the variables or the criteria. Then you have a different random indexed constant. So here you see we have this number that changes depending how many variables we are using. So now for this example, we are going to do 1, 2, 3, 6. Okay, so the one number that we are going to use later on is 1.24. Okay, this is done statistically. We put it in our equations as it is. So,
Those are fixed numbers.
yes.
Okay, and one more question.
Mhm.
Why did we choose 6? Our variables are 7. and elevation.
Excuse me. I missed something then.
Oh, okay.
No. It was 7, right? Yeah, oh no. Okay. 1.32. Okay. So, wait. I skipped something in our experiment. Example, excuse me. And I don't want to mess with this. So we have here elevation, land use, land cover, hydrolithological, slope, and drainage density. 5. We skipped, okay, the drainage, the distance to rivers, which is okay because you have the drainage density, okay? It doesn't matter to have so many. What else?
The rainfall.
And the rainfall. Okay. We left out the rainfall. Mm, when Yeah, we left out the rainfall because sometimes it's very difficult to find some data, okay, about the rainfall on a specific area, depending the area. That I'm giving a thought. It would be better to have this example with rainfall instead of elevation, to be honest.
Can I say something?
Yes.
In at least in my mind,
Mhm.
I would skip rainfall also because then I would use it in a second step, saying that if the rainfall is, for example, 1, this will be the result. If the rainfall is 2, this is going to be the result.
You mean to separate it in order to not have
Yes,
many variables on the same time and do
because
it stagely?
we are not sure about the rainfall.
That's true. There's
So
high uncertainty.
it's something that it will happen. We don't have
Well, the question here is in case we have a flood, so which means
yes.
that you have intense rainfall.
Okay. Yeah. Okay.
You take these assumptions from this assumption from the very beginning, let's say.
Okay. Okay.
So you do have rainfall, and you do have that much rainfall that it's going to flood. So how much flood, where I might have this kind of flood? This is the assumption in this kind of case. But I excluded it is not in order to make it a little bit smaller, okay, in order to deal with on time. But what you said was okay, as you can make different, let's say, or in different, yes, as I show you here, in different stages, this kind of modeling. So you could have another level 4, let's say, okay, with the result from the higher one, the upper one, combining together and then having multiple combinations. And I will let you know. So here we are working with the matrix of the physico-environmental. That's why you see below the PE is the physico-environmental factors. Okay, so excuse me, I have it also entitled. Perfect. So here we deal with whatever is here on the level 2, physical factors. Okay, so another kind of matrix, which is this, we will create for the socioeconomic factors. And later on, because we have decided and concluded with the weights, we will combine all together in order with the same numbers that we used in order to create the vulnerability assessment. Okay, so if we can imagine it as a map, from here we will have to create the physical factor map, the socioeconomic factor map, and then those two maps, those two values, they're going to join in order to create the flood vulnerability assessment. Okay. So, as I mentioned, the elevation, and I will put it with the blue color, the elevation to the elevation is 1. Okay. Before, maybe, before proceeding with putting numbers and make it a little bit more fuzzy, maybe we will see the equations that we are working on. So the VP, maybe the weights here is the division between each row eigenvector to the total eigenvector, the total sum of the eigenvectors. So the VP, which is the eigenvector, is the multiplication of the values in a row. Okay. Excuse me, but my mathematic English are not very well developed, let's say. On with power 1 to 5th, 1 to the number of the of the criteria, 5 in this case. Okay, so if it was 7, for the eigenvector where would be 7 multiplications with power 1 to 7. Okay, this is how the in algebra the eigenvector is calculated. So you can put it like that here in this Excel and then having automatic the calculation. The weights now is, as I mentioned, the division of each eigenvector per parameter to their total sum. Okay. So these are the weights that we want to use. So now we continue with the numbers. So let's put the easy first. Okay. So elevation to elevation is 1. Look with look is 1. Hydrolithology is 1. Slope is 1. Oh no. I don't like this. 1, 1, and drainage density with drainage density is 1. Below, you see the same numbers normalized. Okay. And when I'm talking about normalization, I'm talking about the as vertically the division of its value to the summarize on the vertical. Okay. So our, let's say, maximum number that we're going to get here is 5 in the normalization. Okay. So the maximum per criteria is 1. So 5 criteria, 5. Okay. So this is the normalization. Let's proceed. Now, the land uses to the elevation. Or we can do it horizontally, whatever you want. The elevation to the elevation is 1. The elevation to the land uses land cover. How much, let's play, how much important do you think it is? And the how much, that's why I have here this note. We can see it here. So, what do you expect? how you would evaluate. So our question is flood. Okay, we are going to get a flood. How much important is the elevation towards to the land use land cover to get a flood? If I
I
am
would go,
Mhm.
I would go less than land use land cover.
So it's not so much important.
Yes.
Okay. Another one?
I would say 7. Very strong importance.
So it's more important the elevation to the land use land cover.
Yes.
So let's do an assumption. If I have a town on higher elevation and a town which is the same land use land cover on the low elevation, let's say, which town will be more prone to flood?
The low elevation.
Hmm?
In the low elevation.
Okay. This is how you will have to work, I mean, while thinking on this kind of tables, okay? Doing some assumptions, doing some to see each case under your first question is how it works, okay? Okay, we said that is lower, but I need a number. So how much lower is the elevation on, or now that we mention is lower, we can do opposite the question. How much important is the land use land cover to the elevation? How much more important is? Equal important, moderately, uh, very essential, very strong, or extreme, or something between these values.
Moderate importance.
3.
Yes.
Okay, let's go with that. So, 3, excuse me, not 3, not here 3. The question was the land uses land cover to the equation, so the 3 goes here, and here it goes the 1 to the third. Okay, this is how you start filling the table. Okay, we continue with the question. The elevation towards the hydrolithology vulnerability. Which is more important? The elevation or the hydrolithology vulnerability? The hydrology vulnerability, I mentioned before, is how the soil, let's say, the rock or the soil, is absorbing the water. Also, you have to keep in mind where, on which altitudes we have um, more floods, on higher altitudes or lower altitudes.
Lower altitudes, but we have in lower altitudes we have more floods. But in lower altitudes, I don't know what kind of rocks are. I think, for example, I in my mind I see that in high elevation the soil is more rocky, so it's not absorbing.
Mm-hmm.
In low elevation, it's more like bare soil, like I don't know, even sand. Okay.
Let's loose material, let's say.
Okay. So it's more. It absorbs more water, I think.
Okay. Mm-hmm.
So
But which of these is more important to get you a flood?
I would say the hydrological factors are more
Me
important.
too. Me too.
Very good. So first you answer which is more important, and then how much more important it is. Okay, this is how you work. Also, now that we pointed that the hydrolithological is more important to the elevation, let's go here to fill it. So, how much? Moderate, essential, very strong. Don't get afraid to give higher values. Don't be afraid. I mean, in general,
I would
I
go
say.
for 7 or 9.
Okay,
I think 7.
we're playing now. I agree with everybody, except if it is the opposite. So, okay, anybody else has a different opinion? I mean, 7 is very strong importance. We agree. Okay, good. Let's put 7. So we put here 7. So here we put 1 to 7. Good. Elevation to slope. I remind you that most floods occurs where you have changes in the slope from higher angles, slopes, let's say, to lower slopes. This is the place where most floods are occurring, start occurring. Higher slope means higher velocity of the water. But
So
also elevation means smaller rivers. In higher elevations, you don't have very big rivers, you have smaller rivers. And the slope is generated from the elevation.
I would say slope is more important.
Good. How much?
7 again.
Ah, much more important.
Or 5.
Moderate. No, essential.
Essential, yes.
Anybody else?
I wanna
Yes.
say a 9, extremely important, because
yes, me too. I
that
would go.
controls how fast the water gonna move and where it's gonna go.
9, though? Huh?
9, yeah.
Okay, let's go with that. It's fun. So, slope
Can
9.
can I say something? Maybe I don't understand something.
Yes, yes, of course.
When the slope is very low,
Steep.
yeah,
Low. Yes.
not steep, low,
Mhm.
like flat.
Yes,
This is where the water stays. It
it's
doesn't move,
true.
it stays. It creates the flood.
That's true.
So it's the point is how do we define the slope? Steep or not steep? This is how we will give the
We don't, here we don't put the data. Here we don't put the data. This is data. What you mean now? We
yes.
don't put the
Oh,
data here. We see which is the most regulatory factor.
okay, okay. Yes, yes. Okay, I understand. Yes. So it's very important. Yes, extremely important. I would go.
Let's go with 9. Yeah. So 9 slope to elevation. So elevation to slope is 1 to 9. Okay. So you see now how it's going to is filled. Okay. And final one, elevation to drainage density. So I remind you, drainage density is the length of the rivers to the area that the rivers passes.
the length of the river.
Yes, it's the length, how many, let's say, but it's not a number, to be honest, is calculated in kilometers per square.
So it means also how many rivers they are.
Yes, but not in the number. I mean, it could be one river, doing meander, for example. So it's one river, but higher length. That's why it's length per area as a number.
I'm confused. If it's a long river, there are many places that the flood can occur. That maybe it's not an area that it's important. Okay.
But in order to have
If-
this, you have lower elevation, right?
Excuse me.
But in order to have this, what you mentioned, you need a lower elevation. You cannot have big rivers with meanders in higher elevations.
Yes. Well, it's more important than elevation, of course. I think yes, it's more important. But I don't understand how this DD is defined.
How much? Okay. Maybe you don't get the feeling, maybe because they're very connected, they're very close. I don't know.
I mean, in the same area, if we have one river, it's different than having three rivers. Okay.
It depends the length.
Okay. I'm not a geologist, so I don't understand it. So, okay, I just accept it.
You may have one river, but a small one, and still the area is an area. But you may have a bigger river, or you may have more small one rivers, which their length, total length is more than a higher one big river. I mean, that's why we count it as the total length of the rivers. It doesn't matter how many they are. It matters their length passing to a specific area. This division, let's say, is the drainage density.
Okay. So it's I would go for 7 or 9.
Extremely.
Yes.
Okay. Of the drainage density to the elevation, is the elevation to the drainage density.
Uh, uh, the drainage density is 9 times more important than elevation.
Okay.
So
Anybody else? We have 10 more minutes. Come on. Let's go a little bit faster, guys. Sorry. Um, Anybody else? Another prize to do? Or we proceed with Vasilis? Okay. For me, to be honest, I wouldn't go with that much because the drainage density is very connected to the elevation. Okay, higher elevation does not have a high, cannot have a high drainage density. Okay, but I don't want to change, let's say, your feeling. So I will put here 9,
no,
and here,
for me, it's a feeling because I don't know the theory behind it. If you know better, it's okay. Put a 5, put a 3, I don't know, whatever.
okay. To be honest, I would put a 3.
Okay. So
Okay,
let's put 3.
so 3 here and 1/3 here. So now that we excuse me, finished with the first row, we see that we do have the first eigenvector 0.28, and okay, the weights are not finished yet. Okay, but we do have the first eigenvector. Let's proceed a little bit faster with the rest. So the land use land cover, we have finished with the elevation, etc. So the hydrolithology, the land use land cover to the hydrolithology, how much, which do you think is the most important and how much? Come on, guys. I won't finish until we complete the table and see how it goes. Okay, so Let's do it in the time.
Hydrolithology again more important.
Okay, I agree. How much?
5, I would say, essential.
Okay. Yeah. 1 to 5. Let's go. Land use, land cover per slope.
Slope, more important.
Okay, how much?
7, or we can use the other numbers, 2, 4, 6, 8, that we are between,
Okay.
with 8.
Ah, not extreme, but a little bit. Okay.
Yes.
Yeah, why not? Guys, for me, it's fun, this. I like this, very much this procedure. It's like solving a puzzle. Land use, land cover to drainage density. Who affects more?
The land use.
I agree. How much?
5.
Okay, so 5 here, 1 to 5th here. Good. Uh, Hydrolithology, now vulnerability to slope.
The slope is more important, I think. And I would say 5. I don't know. 3.
I would go a little bit less, not 5. I would go to 4, to be honest.
Okay.
Okay. Hydrolithology vulnerability to drainage density.
4 or 5, maybe.
More important.
Hydrology, it's more important.
Okay, let's go with 5 that you mentioned. Okay, so here's 1 to 5. And last one, slope to drainage density.
Slope, more important.
Okay, how much?
I would say 5, not very high.
When? Finished. Let's see what we got and see how to read this. So we have all these eigenvectors here. So the total sum, the summarize of our eigenvectors is 7.99. This is just algebra, okay? But the weights here, it means, and they are not, and they are normalized, okay? I remind you that is the division between each eigenvector to the summer, their sum, so they are normalized. So we here got more influence of the slope towards all our 5 parameters, okay? So if you do it times 10, times 100, you get it as a percentage, okay? So here we are 54% of the slope for the flat vulnerability, 6% of the drainage density, 27% of the hydrolithology, 10% of the land use land cover, and only 4% of the elevation. Okay, this is how weights ends. So, works, excuse me, works. So, below we have the, and I will do a zoom now. Below we have the normalization of our factors. Okay, so the normalization is working vertically. So the elevation, okay, we get 1, so it's correct. Their summarize is 5. Yes, we have 5 factors. That's why their summarize here is 5. Okay, and here we are getting how the evaluation, okay, of our model is working. So here we have the priority vector. The priority vector is the average, okay, of the normalized values that we used for a specific criteria. Okay, this oh no. Okay, I know I did something. So this is the priority vector. You need the priority vector in order to calculate the overall priority. The overall priority is the multiplication of each value of a criteria times its weight. Okay, and then their total summarize. So it's 1 for the evaluation times its weight plus the land use land cover. Okay, the value towards the land use land cover times the weight, and etc. So I don't know if you see the colors in order to do the one-to-one matching. And this
I think
provides
it's not horizontal, it's vertical.
is vertical and horizontal. It's okay. Let's see. Let's say is the values for example, the overall priority for the land use land cover, which is 0.63, it's provided by the value, not the normalized, the value that we put it, times the weight that it got this criteria at the end. So it's the land use land cover, the times the weight of the elevation plus the value of land use land cover times the weight of the land use land cover that got at the end, the 0.10, plus the value of land use land cover times the weight of the hydrolithology that it got in the end. Okay,
Yeah.
this
Yes.
is how it goes, because the weights now are for the each specific criteria, and this is how you calculate the overall priority. And this you calculate that in order to use it for the rational priority, which is the division between the priority vector and the overall priority. That's why we calculate this. Okay, and this is the rational priority, E. Rational because of our thinking, let's say. Okay, and finally, you also do the summarize in order to calculate the L max, which L max is the summarize of the rational priority divided to the number of our criteria, 5. Okay, so X L max, which is the rational priority towards the divided by the number of our criteria, and the consist the come on this number, the Ri, okay, excuse me, no, the Ri is no, is at the end, excuse me, the consistency index, which the CI is the Lmax minus the number of our criteria divided from the number of criteria minus 1. This is the equation. And in order to finalize it and make our consistency ratio, which is the characterization of our thought, the approval of our thought, is the CI divided by the random index, the Sati random index. Okay, so until here, until the CI is our work with the eigenvectors and these all calculations, and at the end we have to divide it to the random index, which is standard. Okay, in this case we used 5, so 5 is 1.12. Okay, so our final CR, consistency ratio, and you have to be very happy with that, is 0.08. In order for our thinking and model to say that it worked, we need a consistency ratio below 0.1 or 10%. So we are here 0.08. So what we built, it is in the consistency ratio approval. So we can keep this model plus build another model and then start and combine them.
Can I ask something?
Yes.
0.08 actually means that we have 8% of probability to have made a mistake.
To be honest, this is a very good question. I'm not sure if we can make it as a percentage to say this is our accuracy, but we can say that it is under the acceptable.
Because you said
order.
before, like 0.1 is 10%. So
If we
0.
can say, if it is a percentage, yes, we say that we are at 8. Of course, we could build the same model to get lower values. Okay.
Yeah. Okay.
The lowest, of course, the better. But still, you are good, so you can keep this rational thinking.
Okay.
I don't know if you liked it. For me, it's quite simple, let's say. The algebra is very specific for the eigenvectors and all these parameters. They're very specific. Okay, I just built it in a Excel, of course, to work it correctly. Okay. I will stop now because you have also a second, you do have a second class, right?
Yes.
I
But
mean,
we don't know.
it is online.
It is online, but we don't know
Yes.
the time.
It's always the same
1:45.
time.
No?
No?
1 και 4.
1 and 15. So, yeah, I took some time from your break. I will provide you some instructions, some material to read about the models and the AHP. And one exercise that you have to do is, of course, you can do it alone, this specific part, but also you will have to do the socio-environmental part, socio-economic, excuse me, part, and then you will have to join these two models in order to create the higher model and answer the question, where is the flood vulnerability? Okay. in the level of the level of the table. Later on, we will see how we spatially analyzing these models in the GIS and visualize our data. Okay?
Okay. Can I ask a question?
Yes, Vasily, please.
We fill in the the table for the socioeconomic factors,
Mhm.
and we have to join the two tables.
Mhm.
There are going to be actually two variables.
To be honest,
So Eigen model is not working with two variables.
you will have some weights, let's say, okay? You already have some weights, which you're going to use them later on for your analysis. But in order to join two tables, you will have to evaluate between those two, the physical or the social environmental, which is more important for you, okay? To put some weight also for that. And this will affect their interaction.
Okay, we will see.
Or you can create a larger table. You can put the fixed numbers that you have already done from the previous separate tables, and then try to, let's say, correlate only the new empty spaces that is created between the physical and the social. This will be fun. It will
Okay.
be fun because different people see it with different perspective,
Mhm.
which is more important.
Okay.
Are you going to share the Excel as well and the recording?
The recording always, you know, it's I upload them on the E-class already. It is uploaded, the previous one. The Excel, I'm not sure because I want you to read the whole algebra and do your own mathematics. To be honest, it's very easy to delete all these numbers and give it to you. Okay, for me it's very easy. But while constructing this Excel, let's say, or writing down the equations, you know, you understand deeper about these equations while you are reading these equations. So I think it's better to DIY.
Okay.
But I
Okay.
will provide you with the papers who have these kind of equations there, for sure.
Panoletria. I don't know the word in English.
I told you, I tried to be smooth here. I mean, while we started this semester, I don't know, but I cannot postpone it. I'm sorry.
Can I ask something
Yes.
irrelevant? The grades from the previous
Mhm.
the grades from the previous course, do you upload on the class?
Yes, where I will
Have
upload
you
them. Okay, give me a moment to stop the recording.